Okay, so I'm going to go through 6 solvolysis reactions. The instructions are to write the major substitution product of each of the following reactions. So this is just your basic, I think, SN1 or SN2. The way we're going to determine whether these reactions are SN1 or SN2 is by what how many carbons our alpha carbon is connected to, and as you know with the SN1 reactions, our alpha carbon is connected to around 2 or 3 carbons depending on the nucleophile. In this case, since all of the carbons are tertiary, the alpha carbon is too hindered for an SN2 reaction to happen. So all the following reactions will be SN1. And the most important part of these problems is to actually recognize your species. So our alpha carbon is usually connected to our leaving group, or pretty much always connected to our leaving group, which is a bromine in this case. Most of our leaving groups are halogens, so like bromine, chlorine, iodine. These are all good leaving groups. And so we know our leaving group, we know our alpha carbon, and we know that this is our nucleophile. So now all we have to do is write out the major substitution product. So we know that in SN1 reactions, it's a two-step reaction where first the leaving group leaves and then the nucleophile attacks. So for these problems, we don't need to show the steps. We're just going to write the product. So our product is going to look something like this. So as you can see, the leaving group has left, which is why it's not drawn here. And now all we need to do is take the nucleophilic atom and attach it to our alpha carbon, which is our oxygen is our nucleophilic atom. So it's going to look like this, with that attached. This hydrogen right here, as you notice, this oxygen here has no charge because it's connected to 2 different groups. Here the oxygen is connected to 3 different groups, so it has a positive charge. So in these SN1 reactions, what actually happens is this hydrogen deprotonates and it kind of leaves, so oxygen can have that 0 charge. It wants to have no charge at all. Generally, when doing a substitution reactions, you want your product to have no charge, if possible. Do not force the charge, but if you can deprotonate, that is what you would want to do. Okay, next problem. We recognize that this here is our alpha carbon, this here is our leaving group, and since we have 2 carbons attached here and 1 there, it's a tertiary carbon. Our alpha carbon right here is a tertiary carbon. What that means is it's going to be SN1, just like I've said before, and our leaving group is going to leave, and our nucleophile is going to attack. So our product will be exactly the same, except the bromine won't be there, and our nucleophilic atom will be attached to the alpha carbon. So that is going to look something like this. I'm going to draw it below because it might be a little too big. With this carbon now attached to the nucleophilic oxygen, and that's our product. Alright, on to the next problem. Here we have a cyclopentane that has 2 substituents on the first carbon if we were to use IUPAC nomenclature. So our leaving group is our chlorine. This right here, that carbon right there, is our alpha carbon. So chlorine's our leaving group, so we're going to have a product that looks something like this. There's our pentane, there's our ethyl, and here it's attached to the nucleophilic oxygen with the CH3. Once again, this oxygen has a hydrogen on it, and of course it's going to deprotonate to preserve that neutral charge. And so this right here is our product, if I'm not mistaken. Alright, next problem. Now we have this funky looking cyclohexane attached to this carbon, which is our alpha carbon, because it's attached to our leaving group here. This is our alpha carbon, and this is our nucleophile. So what we're going to have is a nucleophilic substitution, just like all the ones before. And also remember, there's a carbon here, so it's a tertiary carbon, SN1, just as I've stated before. And our product looks something like this. Our bromine has left, and we have an OCH, as this H gets deprotonated so that our oxygen retains that zero formal charge. Alright, second to last problem. Here we have carbon, it's tertiary, this is our alpha carbon, this is our leaving group, and this is our nucleophile. Hold on a second, what's this here? This is a D that stands for deuterium. What that means is I think that's a isotope of water, a heavier isotope of water, so we're just gonna treat the D as if it was an H. So just treat this like as if it was H2O and do the reaction just as you normally would. So what we're gonna have here is a CH3, and it's here, this carbon's attached to 3 methyls. Our chlorine is for the leaving group, so we're gonna have OD2, right? Wrong. This oxygen is attached to 2 Ds. That means that it will have a positive formal charge, and since we don't want a positive formal charge, we'll have to take off the 2 and make it a 1. And now we have the correct product. Alright, similar thing here where we have an OD, except this is now our nucleophile, and this is our substrate. Here are we have our alpha carbon, we have our leaving group. Actually, the substrate of both of the problems is very similar. Actually, it's exactly the same. So now let's carry out this reaction. We're going to have the exact same primary steps. Actually, I shouldn't call them steps. Also, don't ever draw this as CH3, or write it as CH3, because this carbon is attached to this hydrogen when written in this form. So whenever you draw a little line, you always want to write H3C for those picky TAs. But if you don't draw a line, then you can write CH3 connected to a C. However, you always want to show that the carbon is bonded to another carbon, just for a little clarification there. So we have that right there, and also this carbon is now attached to our nucleophilic oxygen. Right, so our oxygen is attached to this cyclohexane, which I'm going to drop off to the side. Cyclohexane has an OD, and this thing right here, which, sorry, excuse me. Also, this oxygen is attached to a D. Once again, 3 bonds on an oxygen, not going to happen because we can deprotonate this, although it's not a proton. I'm pretty sure we can get rid of that D right there, just because it's an isotope. Even though, how should I explain this? Okay, it's a hydrogen. It's just an isotope of hydrogen, so you can deprotonate. So we are going to get rid of this D right here to get rid of that positive formal charge, and we'll end up with this product. Actually, the interesting thing to note here is that this hydrogen right here is actually not needed. It's implied that all of these carbons have other hydrogens attached, so actually I don't think it is necessary to draw even that hydrogen in. Basically, your product could look just like this O attached to cyclohexane. And that's all for this video.